All right, so we have a wind that is blowing at 45 miles per hour. The wind is blowing in a direction 30 degrees south of west. So I want to find the westward and the southward components of the wind. Okay? Perhaps you have like a southward facing wall and you want to know what kind of force that wind is putting on that wall. It's not like, because it's not blowing completely southward, it's not like 45 miles per hour is blowing straight against the side of the wall, right? It would be kind of shearing off, so it's not going to be a full force. For this one, we're 30 degrees south of west. So I'm going to draw myself a compass, but south and west are the two sides I'm most concerned with. So I'm going to make it kind of look like this, right? North, south, west is over here, east is over here. And my vector should be going 30 degrees south of west. So this angle right here should be 30 degrees. Okay. Now, this one is not asking us to add vectors together. It's asking us to, it's saying basically they've already been added together. I want you to break them back apart. Okay? So what we've got to do is we've got to make a parallelogram here. We want to know the south and the west components. So you're going to make, these are going to be right angles. So your south component will be straight down. Your west component will be horizontal here. So we're going to draw it like this. And then our southward component will look like this. I'm going to label it S, although S is not the best variable in the world because it starts to look like 5. I'm going to call it that anyway. And then I'm going to label my westward component W. So this side right here is going to be S also. This side right here will be W also. We will have right angles for all of these because south and west are going to be perpendicular to each other. So you can look at whatever triangle you would like, but I am going to focus in on this triangle right here because that's the one that has that 30-degree angle. I know an angle of that triangle. And I forgot to label. I need to know a side. What side do I know? I know that that hypotenuse right there should be 45. So you are going to focus on this one piece at a time. So I either need to find S or W first. Lucian, which one do you want to find? S or W? Okay, so we're going to find S. Would S be my opposite, adjacent, or hypotenuse? This is opposite. And 45, hypotenuse, right? So opposite and hypotenuse means that we're going to use sine. So we're going to have sine of 30 degrees equals our opposite, which is S, over our hypotenuse, which is 45. And to solve that, we just need to multiply by 45. And, that's my, let me pull up my other calculator here. I'm going to use the calculator. You can use it. Well, let's use our calculator. Desmos works too if you got to use it at home, but let's stick to calculator right now so we don't have to get the computers out. All right, so 45 sine 30 is going to give us 22.5. So S equals 22.5. And S is the length of a side, right? What am I measuring that in? Miles per hour. So the southward component of the wind would be 22.5 miles per hour. Now you're going to go back and do pretty much the same thing, but with the westward side. Okay? The westward side is that opposite, adjacent, or hypotenuse. It's adjacent. So you got options here. You could do tangent because you know the opposite side now, but I would suggest doing cosine. So cosine of 30 degrees is going to be W over 45. And you just have to multiply both sides by 45. And 45 cosine 30 is going to give us 38.971. You could also do that at that point, yes. On this one especially, it's perfectly fine, Luke, because 22.5 was an even number. The only thing I would caution you about using a squared plus b squared equals c squared for is that if this was like a big long decimal, you got to be careful with your rounding. It might throw you off a little bit, but you could also do that because you already know two of the sides. So our westward component is 38.971. Okay, questions? If you find yourself taking physics, which I love physics, it's just science math is all it is. It's mostly math. I love physics. I've forgotten a lot of physics because I don't use it every day, but I did love that class. If you find yourself taking physics, you will do whole sections on vectors, and there's a lot of different ways you can deal with vectors. I am coming at it from just a purely triangle perspective, okay? If you're going intensive on vectors, there's a lot of different ways you can deal with vectors. Everything I'm showing you would still apply in physics, but when you take physics, they're going to show you some other different ways of dealing with this stuff as well. We are doing it as a small part of the sines and cosines unit, and that is why we're doing it the way that we're doing it. It's a separate unit in the textbook that I had. So I have done it before. I don't know that I've ever taught it completely by itself. But when I was going by what was in the textbook, I would call it Unit 8 for that. So that's probably what happened there. So, but in our textbook, which has like way too much stuff to cover in one semester, there is a whole unit on vectors, and they go into more detail on different ways you can deal with vectors. But we're just approaching it. We're putting it in with triangles and dealing with it this way. Here. All right, so a sled is being pulled with a string. The string makes a 62-degree angle with the ground. The person pulling the sled is exerting a force of 4 newtons. What are the horizontal and vertical components of the force? So, if we think about pulling a sled, right? If you're thinking about maximizing your effort, right? You want your effort to do the most good. If we are pulling the sled along the ground, so here is our sled right here. We have a rope that makes a 62-degree angle with the ground. It this is our vector. I'm going to put an angle over here on the end, right? And then here's our person that has decided the best way to carry this, to drag the sled along, is to put their hands up in the air like this as they carry it. But that gives us a vector here. So this is a similar problem. We've got a resultant vector is what we've been given. Right, so this sled, as you pull the sled along the ground, your goal is for the sled to move horizontally, right? You want the sled to move horizontally. So the most efficient way to pull this sled would be if you only pulled it with a horizontal force, right? Any upward force is just wasted, right? Because it's pulling up on the sled. If it's a light sled, it's even going to pull like the front of the sled up off the ground. So it's wasted energy. However, in order for you to pull with a completely horizontal force, you have to get down on the ground and crawl on your hands and knees to do that, right? That's also not going to be the most convenient. So you know, you kind of have to give up some of your efficiency for the ease of being able to do it. It's much easier to pull the sled this way. So we're going to treat this kind of like our XY axis is right here. And so I kind of got ahead of myself drawing that green vector there. This blue vector is my resultant. So I'm going to make a parallelogram for it, and that parallelogram needs to be a rectangle there with it's not the best rectangle in the world, but that's a rectangle there. So that we've got a horizontal component, and we also have a vertical component. And when I draw this, I just happen to draw it with like everything to the right-hand side. There's no reason we couldn't draw it the other way, like they're pulling the sled that way instead. Everything's backwards here. So I just chose to draw it this way. It doesn't matter which direction you draw. So since I know this angle right here is 62 degrees, right, I have a vertical and horizontal component, so I'm going to call this right here V. I'm going to call this H just so I can remember it's vertical and horizontal. Our hypotenuse, we would label it with 4 newtons. That's our force. And so if this side right here is V, this side right here is also V. And this would be a right angle right here. So we're going to break this down like we did the last problem. We would begin by looking for either V or H. It does not matter which one. Emma, which one you want to pick, V or H? V. So if we're looking for V first, this is my opposite side. 4 is my hypotenuse, and I must use it because it's the only side I know. So that would be sine of 62 degrees is going to be V over 4. And I will just multiply both sides by 4. So 4 sine 62 is giving me 3.53. So 3.532 newtons would be my V. Then Luke, if we were wanting to find the horizontal components, okay, how would we set it up?
You do cosine 62 equals adjacent.
Okay, adjacent, which is our H over 4. We will multiply both sides by 4. 4 cosine 62 is going to give us 1.878, as Luke said. So the person's exerting 4 newtons. It is causing there to be a 1.878 Newton force horizontally and a 3.5 Newton force vertically. So this is not the most efficient use of that force, right? Because the horizontal force is what's actually doing the work you want it to do. So if our stick figure took their arms and did this, and that angle was lower, that would make them more efficient, right? Here, so if that angle was lower, another way you could achieve that is like if you had a longer string, that would make the angle less because you would, rather than the sled being right here, if you had a longer string, it'd be way over here. And so either one of those could cause there to be a lower angle, which could make you more efficient. Of course, there could also be problems with the longer string as well. It's going to get all tangled up under your sled when you're trying to go down the hill. Slow you down. It's not really good. So, questions? And everything obviously you're not going to be, taking measurements on yourself as you're pulling the sled up the hill. But, a lot of the stuff can apply in more important contexts. We're just kind of having to simplify some things down here, and sometimes I'm the one making up the problems, and I don't have the exact context that like high-level engineers would be using there. So, but you can imagine where this could apply in other things. If you think about things like when they're designing like machinery, like let's say an excavator or something. You got that arm. It's got all those different joints and stuff. You got all kinds of different forces there that have to work together to produce the right force to dig something up. So in the design of something like that, I think Jack was telling me that he took one of the classes he took through NCCSM was like a biomedical sort of thing, and they were using vectors to look at like forces on knees for like knee replacement sort of stuff they were using. So like there's lots of places this can apply. I'm a math teacher and lack the specific knowledge to give you in great detail where it will apply, but you can go really far with vectors. If you take even I had physics 1 and 2 in college. You could major in physics and then you would really get crazy with stuff. It can get really intense, like the places that you can apply this. But we're just getting like a base introduction to it here. And that's as far as we're going to go. All right. This is another like naked problem. No context. This is just, practice sort of problem. So we've got a magnitude of 3, direction of 0, and then a magnitude of 50, and we need to find magnitude and direction of the two added together. So this one's going to be a little bit different than the ones we've done so far because these two are not at 90-degree angles to each other. So the problem is going to be a little bit different. So whenever we draw these vectors, we really only need to see mostly the first quadrant here. So we'll understand it even a little better when we do unit circle stuff. But the positive x-axis, this is 0 degrees, right? And then you go counterclockwise to name your angle. So like this right here would be 90 degrees. We're not using it for this problem, but it'd be 90. Then over here we'd have 180, and then this would be 270. And then if we went all the way back around, that'd be 360, right? So whenever they give us a direction, they are assuming that you're drawing your vector with its endpoint right there at the origin, and then that angle is from that positive x-axis counterclockwise direction. Okay, and they give us pretty easy ones here because we've got a 50-degree angle and a 0-degree angle. We're staying in the first quadrant. We're not getting too complicated here. So 3 centimeters, 0 degrees. So 3 centimeters, I'm going to draw it like this and label it 3 centimeters. Then vector B, I'm going to use green for it. It has a 50-degree angle, so about like that. And my vector is a little bit longer than than my 3 centimeter vector, so I'm going to call that 4 centimeters there. We could actually draw this to scale, but for the ones we're going to be doing, this will be probably good enough. Now, I need to use parallelogram. If I'm using parallelogram method on this, which I have to do because I've put both endpoints at the same place, then that means I've got to make a parallelogram. All the problems you've done so far have been rectangles, right? This is not going to be a rectangle. So if we draw out like a line parallel to the blue vector and then a line parallel to our green vector like this, it does not create a rectangle. So these are going to be a little bit trickier. We're not going to be able to use regular trig for this. We have to use law of sines and cosines. Now, I didn't label my angle. I should have here. This angle, this whole angle right here, that was 50 degrees. And I know if this side is 4, this side right here is 4. And I know if that bottom side is 3, this top side should be 3. Okay, so this angle right here, angle across from 50 would also be 50 degrees. You are correct.
The other two are 130.
Yeah. So the angle you really want to know is one of these obtuse angles right here. Because the side that you want to know, the magnitude of this vector right here would be x, right? So you really want to know an angle across from that. So if we're looking at the parallelogram here, you are correct. Both of these angles have to be 50. These other two across from each other have to be equal to each other. So you're going to have 130 right here, and then that angle over there across right here, that would also be 130 degrees. So you will find that what we call consecutive angles, not the ones across from each other, but the ones that share a side, they have to add up to 180 in a parallelogram. So if this angle right here is 50, then this angle right here has to add up to 180 with it, which means it'd be 130. And if you add all 4 of them together, they have to add up to be 360. Okay? A lot of times getting that angle is where we really have the most trouble. Sometimes that can be a little difficult. But think about the angles of that parallelogram. Sometimes you may not even want to draw in your resultant vector until you're done getting the angles of the parallelogram. Yes? The others had 2 vectors as well, but all the other vectors we've dealt with so far have been perpendicular to each other. So whenever we made it a parallelogram, because they were perpendicular, the parallelogram ended up being a rectangle. These 2 vectors are not perpendicular. So when we make them a parallelogram, it has to be a, like slanty parallelogram, not a rectangle for those. So the rectangle is like technically a parallelogram as well, but it's a specific type, but it's because we started with vectors that were perpendicular to each other. In this case, because they're not perpendicular, that's why we end up not having a right triangle here. Okay. All right, so if I look at this triangle right here, you could look at the top or the bottom, but I would suggest the bottom because eventually the angle you want to have needs to be between the positive x-axis and the vector, so I would pay attention to the bottom. So if I want to find magnitude first, what would I have to use if I'm looking at that triangle? Is it going to be law of sines or law of cosines? I've got 2 sides and the angle in between, so this is going to be law of cosines. So I would say x squared equals 3 squared plus 4 squared minus 2 times 3 times 4 cosine 130. And 3 squared plus 4 squared minus 2 times 3 times 4 cosine 130 is going to be 40.4269. But then I have to take the square root. So square root there is going to give us 6.358. And that is centimeters. That is my magnitude. So the length of the side gives you your magnitude. It also asks us for the direction, which is the angle. And so we want to find the angle that this vector makes with the x-axis right there. So it is possible for us to find this other angle up here, but that wouldn't be our final answer. We'd have to do more work if we found that angle. If we find this angle right here, that is between the x-axis and our vector, so that's just going to be our answer. Okay. How are we going to find it? Law of sines this time. It's because we found x. We know what it is now, right? So we have a side and an angle across from it. So we could set this up sine of that number we just found, 6.358. No. Sine 130 over 6.358 would equal, this angle right here is the one we want to know, so we'll say sine of theta over the side across from it, which is 4. And so we can cross multiply there. We'll need to divide by our 6.358. And let's see, that's going to give us 4 sine 130 divided by that number right there. It's better if you keep the whole number in your calculator. So we got sine theta equals 0.481924 and so on. And then what do we do to get our answer for that last sine inverse of that answer? And we get 28.811. So theta is going to equal 28.811 degrees. And this is our direction, that angle. If that is a very good question, Caleb said, do we need to clarify what direction it is going? So for this problem, it was just giving us our directions as straight angles, right? So 0 and 50 degrees. It didn't tell us north, south, east, or west. So in this case, you would just give the angle. So like you would just give the angle as your direction. So if it was like way over here in this quadrant, you wouldn't say 20 degrees south of west. You would just have like an angle, it would be bigger than 180 that would end up over here. So if the problem does not say north, south, east, or west in the problem, do not put north, south, east, or west with your answer. If the problem does say north, south, east, or west in the problem, then you need to give your answer like here we would say north of west here, or north of east here, if we were talking about north, south, east, and west from the beginning. Does that make sense? Good question. All right, questions? All right, we got 2 more to do. But the last one's quick. All right, so I think these problems get kind of neat. Well, they were already kind of neat, like the airplane flying and then it hits a wind that knocks it off course, right? You know, obviously the pilots have like instruments that are, you know, doing stuff for them. In fact, the pilots, I don't think really even fly the plane much anymore, unless they have to. So, you know, the computer is driving your plane and probably making these calculations. But the principle applies. Somewhere, somebody who programmed that plane to fly itself or do whatever, you know, understood these concepts and applied them in some way more complex than I'm able to address. But the idea you can kind of see. So everything you've seen so far, your plane was always flying north. The wind was always directly west. We know that's not the case. A lot of times the plane is flying northeast, and the you know, direction of the wind might be southwest or something. So we could make it even more applicable to situations by looking at something like this. So airplane is flying due west at a velocity of 120 meters per second. Wind is blowing 20 degrees north of west at 15 meters per second. What is the magnitude and direction of the plane's resultant velocity? So our plane is flying west, but our wind is north of west. So whenever we draw this, we're going to draw a compass, and north and west are the main 2 directions we need to give ourselves some room for. So north, south, west, and east. So plane is flying due west at 120 meters per second. So I'm going to draw that vector pretty long. 120 meters per second. And then our wind is blowing 20 degrees north of west. So this vector is not going to be as big because it's only 15. In fact, I'm not really going to draw it to scale because it becomes too difficult to draw the picture. I'm going to make it a little longer than it should be. So this is 15. Oh, I've messed up my angle too. Let me go back. Let's try that again. Let's make it a little more. So 20 degrees should be a little more like this. So this angle right here would be 20 degrees. So to draw in our vector, we do not just connect your 2 arrows right here and make a triangle. Your magnitude's going to be okay, but your direction is not. So you've got to make a parallelogram. So you're going to make, you know, this one's easy because it's parallel to your horizontal. Then you're going to do your best to make a parallel line right there. It's not perfect, but it's close. I think I'm going to do this before I even draw in the resultant vector. It's going to help me if I know all the angles of that parallelogram. If this angle right here is 20, what is this angle this big angle right here going to be? It's going to be 160. Because your 2 consecutive angles, the angles that share a side, they have to add up to 180. And then if we want to label them here, this has to be 20 right here, and this one right here would also have to be 160. Although we're not going to really need those as much. So my resultant vector goes from the common endpoint to the opposite corner of the parallelogram. And think about what you're doing. If the plane is traveling to the plane is traveling to the west, and the wind is blowing northwest, the plane's going to fall somewhere between that, right? So it would make sense that the plane should go in this direction, right? And make sure you put arrows so you know which way. All right, so we need to know magnitude, which is going to be this side right here. We also need to know direction, which is going to end up being, you could find either angle, but this one right here is going to be the best angle to find, that little tiny skinny angle right there, because it touches west, so we can say that that angle is north of west. It'll be easiest to report. If you find this angle up here, it's no good because it doesn't touch north or west, and you can't tell what direction it is, so you don't want to find this angle. And you never really want to find these over here because they're not the angle of the vector there. So, got to do magnitude first. This one, like the last one, I didn't label this. This is 15. So this side is 15. Like the last one, if we look at this triangle right here, we have a side angle side situation. So we're going to be using law of cosines. So we will have x squared equals 15 squared plus 120 squared minus 2 times 15 times 120 cosine of 160. We will type that into our calculator. And so, yes. Whenever I had my parallelogram drawn, in that parallelogram, the consecutive angles, which are like your angles that share a side right there, they have to add up to 180. So 20 and 160 will add up to 180. So since I know the angle of this parallelogram is 20, this one has to be 160 here. And then, like, these two here also have to add up to 180, so that one's 20. These have to add up to 180. That one's 160 there. Yes. Okay, and we'll square root this. All right, and we get 134.193. And this is our magnitude, which is our speed in meters per second. So you can see it adds, 14 meters per second to your speed, which is if the plane's going far, that's going to make a difference in what time they get there. Okay, questions on the magnitude are setting up so far. We still need to find direction, but. Okay, so now that we have found that magnitude, we can say sine 160 over that number we just found, 134.193, equals, we want to know this angle right here, so we're going to say sine of theta over 15. And we will cross multiply. We'll divide by the 134.193. So sine of theta is going to equal 15 sine 160 divided by that answer. You get 0.0382. And then sine inverse, and we get 2.191 degrees. How would I report that? 2.191 degrees what? North of west. And so this would be my magnitude of my velocity. This would be my direction of my velocity. I incorrectly used the word velocity once in the problems that you were doing. Velocity should include both speed and direction. If I only am asking for speed, I should just say speed. That's just your magnitude. But velocity includes direction, so I know I used that incorrectly. And I may have done it again on something. Yes, we're going to do it. It's going to be super fast. All right, questions on this one? Think about how important this is, because if you are 2.191 degrees north of west off, if you're only flying 30 minutes away, you're probably going to be fairly close to the airport you're trying to get to, and you can circle around and find it. If you're flying all the way across the country and you're 2.191 degrees north of west, you're going to be in the wrong town whenever you get there.
From like Washington to Southern California.
Yeah, you're going to be way off, right? So it's going to be really important. Even though it's something really neat to think about, I had a whole class in college. When you're talking about flying like around the globe, you're actually not even doing flat line geometry anymore because you're flying across a sphere, which means you have to have a whole different geometry to deal with that, where a line is a circle, and it's kind of crazy. I had a whole class on it in college. It was really cool. So
It's like warp.
yeah. Yeah, because like your line's not really, like for short distances it wouldn't matter because it's close enough to flat that it's going to be good enough. But when you start talking about flying, across the ocean sort of flights, like 8-10 hour flights, you can't just use flat on paper geometry anymore. You have to have a different geometry to deal with it, which is cool. I love geometry. All right, so, yes, I said this one would be quick
Yeah, but we got two different magnitudes.
because you have a magnitude of 3 and a direction of 20 degrees. That looks about like this,
You know, literally like the opposite of that.
20 degrees. Yes, and then 200,
This is cool.
200 is all the way over here,
It is.
and it is exactly opposite.
It's just a line. See, subtract 3 feet. Kind of like that's a magnitude.
So this is 10 feet, and this is 3 feet. Okay? So if we are 200 degree angle, it would be like all the way around here. And because those are exactly 180 degrees apart, if we subtract them, they're opposite vectors. So this is like, they used feet here, but this is like tug of war right here, right? Somebody is pulling in this direction with the 3 foot force. The other one's pulling with a 10-foot force. What's going to happen? It's going to go in the direction that has the greater force, and you'll subtract the two. So our resultant vector, you cannot make a parallelogram for this because it's a straight line. You can't really draw it out. Your resultant vector would go in the direction of the largest vector, but you would subtract the two forces, so you'd have 7 feet. So it'd be 7 feet. And they just told us the magnitude was in feet. So it would make more sense if it was like newtons or something if it was force, but they just told it was feet for some reason. So if you ever have vectors that are opposite each other, that are 180 degrees from each other, you just subtract them and it's going to go the direction of the bigger, right? Like tug of war. If we put Emma and Lucian in a tug of war match, right, they will both pull on the rope with equal forces, And physics is going to mean that Lucian is going to win, no matter how strong Emma is. My husband made the mistake of this one time. Because my husband weighed 135 pounds his senior year of high school. He was so skinny. He was 5'11". He was about like Connor Ball, like skinny. He was relatively close to his size. He was so skinny. My cousin Megan, she was clocking in probably over 200. And and so, but my husband was stronger than her, like